Hi everybody, I had a student ask me about work session 16, question 16. So this one asks us to determine the hydroxide ion concentration, the pH, and the pOH of a 0.125 molar carbonate solution. Alright, so the first thing you want to do is to always ask yourself, what is in my beaker? So what's in my beaker? And it said it was a carbonate solution. So carbonate is CO3 2-, right? And is that a strong acid, a strong base, a weak acid, or a weak base? Good. Hopefully you said it's a weak base. It doesn't have any protons to donate, so based on the Bronsted acid definition, it's not a proton donor, so it had to be a base, and carbonate's not on the list of strong bases that we've learned in my course, which are the group 1A and group 2A hydroxides. So in that case, we can deduce that carbonate is a weak base. And because it's a weak base and we want to find hydroxide and pOH and pH, we will need to do a Rice table. And not use Ka, but rather Kb. So first order of business for a Rice table is to write down the reaction. That's for the letter R. So we have carbonate, and these are an aqueous solution, so water is the other species on the left side of the arrow. We're in equilibria, and I always use the definitions to help me predict the products. So carbonate is a Bronsted base. Bronsted bases are what? Proton acceptors. So it gains a proton, and in doing so, it goes from a -2 charge to a what? -1. Good. This is bicarbonate, the key component in baking soda. Remember, it's accepting a proton has a positive charge. So -2 plus 1 is -1. And water, in this case, has to act as a what? As an acid. It's the proton donor. So you'll end up with the conjugate base of water, which is what? Hydroxide. Good. It lost a proton, so we end up with OH, and then the charge is negative. It went from neutral, it lost a proton, so overall it's negative, and we recognize hydroxide as one of the polyatomic ions. So, we recognize it should have a -1 charge overall. Fantastic. So that's R, and then initial change in equilibrium. So we were told that initially it was 0.125 molar. And we do not include liquids or solids in equilibria, and it didn't say we had anything to start off with for the products. And then over time, the reactants minus X, and then products plus X, everything's 1-to-1 with these Bronsted acid-base reactions, because it's only a transfer of 1 proton. So that's why it's -1x or +1x. And then for equilibrium, remember you add up the initial and the change, so you have 0.125 minus x, and then x, 0 plus x, which is x, and then x here. Because we're working with the weak base, we would need to use Kb. Little b stands for base. And remember, with any equilibrium constant, it's products over reactants. And so that would be x squared over 0.125 minus x. And then you could look up the Kb value of carbonate in the back of your textbook in the appendix. 1.8 times 10 to the -4. We're going to assume x is small enough to ignore, so when I solve for x, I get 0.0047434. And you can always double check that it's less than 5%, so that it's a valid assumption that x is small enough to ignore. So you can divide by the initial concentration times 100%, and in this case that's 3.8%. So as long as this value here, basically as long as x is less than 5% of the initial concentration, saying it's not going to change all that much, then you can say x is small enough to ignore it. If it ends up being greater than 5%, then you're probably going to need to do the quadratic or if you end up with a polynomial, then like doing the method of successive approximations that I taught in one of the chapter 16 lecture videos. Okay. All right, but in this case, or actually it was chapter 15 lecture videos that I taught the method of successive approximation. All right, so what does X tell me? I always go back to the Rice table to look for the clues. Looks like X is actually the equilibria concentration for the hydroxides. I already solved that. So the hydroxide concentration, once it reaches equilibrium, is equal to 4.74 times 10 to the negative third molar. POH is equal to the negative log of the hydroxide ion concentration, and so that would be 2.32. And then the pH of the solution would be 14 minus the POH, and that would be 11.68. All right, always ask yourself, does this make sense based on what we've learned in theory, right? Well, if we have a weak base in our beaker with water, we would expect it to be basic overall, right? If there's nothing else to change the pH. Then in that case, we would expect the pH to be greater than 7. And so because the pH is 11.68, that supports the theory that, okay, if I have a weak base in my beaker and that's it, then I should have a basic solution, something greater than 7 for the pH. All right, I hope that helps you to solve these types of problems that involve weak bases. Good luck studying.